let me get things started. Uh, okay, so as I said, today we are going to focus on separation of variables, something that, again, you've seen before in a variety of contexts. We will look at some of those that you've seen before, and we'll look at some that you haven't, and we'll look at some of that you've seen before, but in different geometries. And after I set up a couple of these, I'll send you to your breakout rooms to solve a kind of a toy problem. But obviously, the applications are manifest, so I won't go into too much detail on that. So this is part 3, partial differential equations, just in case you didn't get that. And we'll start with separation of variables. And if you go back to the very first section when we started talking about differential equations, I already laid out the different types, the hyperbolic, parabolic, and elliptical differential equations that your book talks about in the first couple of sections. It's kind of a weird chapter in which the first couple of sections don't really have any problems associated with it. It's all kind of build up. Some of it's kind of confusing, some of it isn't. We're going to start with Cartesian coordinates because, of course, that is the one that you've probably seen before, certainly you've seen before, and is the easiest to manipulate. And we could start with the obvious starting place, which would be the Laplace equation, namely del squared v is equal to 0. Okay. And the idea for separation of variables is to assume a solution that can be broken apart into the different dependent variables for the problem, right? So if we assume a solution v is equal to some function that depends only on x, some function that depends only on y, and some function that only depends on z, then we have del squared v is equal to y z x double prime, right? Where that's just taking the second derivative with respect to x plus x, capital Y, double prime z plus x y z double prime, all is equal to 0. Which means that we can divide everything through, and we get the usual form of x double prime over x plus y double prime over y plus z double prime over z is equal to 0. Right, and as far as each of these equations are concerned, right, that means that these are equal to 3 different constants that are equal to 0. And we know that depending on the boundary conditions, we can choose the appropriate value of the constant. In particular, it's often the case that we select a constant that's less than 0. I won't go too much into detail about the Laplace equation in Cartesian coordinates. We'll come back to it, but it's something that if you look in the third chapter, I think it's the third chapter of Griffiths, that you spend a whole bunch of time on. So that's Laplace. What an equation that you may not have seen is the Helmholtz equation. And that describes diffusion. So in that case, this is the, we'll start with the time independent diffusion, which kind of seems like an oxymoron, but we're looking at an equilibrium condition. So the time independent version of this is del squared psi plus k squared psi is equal to 0. All right, so that means that we can break this apart. If we're in Cartesian coordinates again, we'll have x double prime over x. And I guess I'm just suppressing the variable dependence is assumed is equal to minus k squared minus y double prime over y minus z double prime over z. And in fact, this represents our basically our first separation, right? So we have basically taken the function, we've separated it out into x, y, and z, and we are now trying to solve for x prime. And what we're going to do is realize that everything on the right-hand side of 8.4 is a constant as far as everything on the left-hand side. So we'll let x double prime over x be equal to some constant minus L squared. Okay? And some of this is experience, and some of this is knowing what the answer is ultimately. What that means then is we can substitute that into 8.4 and we get minus k squared minus y double prime over y minus z double prime over z is equal to minus L squared. Oh, this should be A5, sorry. 6A6. And so we now have an expression for y, right? So y double prime over y is equal to minus k squared plus L squared minus z double prime over z. 7. And again, everything on the right is a constant as far as everything is on the left. So this is our second step of separation. So we'll let y double prime over y be equal to another constant minus m squared. And so we get z double prime over z is equal to minus k squared plus L squared plus m squared, which we'll call minus n squared. Right? Then the trick is to go backwards, right? And if we recall that our function psi, which we'll denote with subscripts L and M, function of x, y, and z, is equal to basically x sub L, y sub M, and z sub n. We have the final form that is that y is equal to the sum, the linear combination over L and M of some combination coefficients a sub Lm times psi sub Lm. Subject again to, in this case, boundary conditions. When we look at time-dependent version, we'll look at boundary and initial conditions. And you note that we are only writing this in terms of L and M because N depends on L and M. Right? K is just a constant that's part of the problem, right? So don't forget that these things are all eventually what we're going to, especially when we look at, say, the Schrodinger equation, those things will end up being quantized. But in the context that you have seen already, like Laplace equation, you know that those end up being part of your Fourier expansion. Okay. Any questions about that? Should be stuff you've seen. Okay, so those are two examples. The next example, go back to red, is heat flow, which again is a misnomer, right? Because heat is thermal energy flow. So this is energy flow. But we'll use the vernacular here. Namely, this is del squared is equal to some constant, 1 over alpha squared times du dt. So you note that this is a mixed, in a couple of different ways, this is a mixed differential equation. First order on one side, second order on the other side, where u of, say, R and T is our temperature. Okay. So in this case, we're going to assume a solution then that breaks this apart into spatial and temporal terms. So assume a solution U is equal to capital F of X, Y, and Z, and capital T of T. All right. So we've separated out basically space and time dependencies. And then if we move ahead, and again, we're still looking at Cartesian forms of this. We have our capital T times del squared F is equal to 1 over alpha squared F times just the single derivative with respect to time. And recognize too that these are all not partial derivatives, right? The whole point of separation of variables is not to do the partial derivatives, but to do the exact derivatives. So that means that we can write this as 1 over F times del squared F is equal to 1 over alpha squared 1 over T dt dt. And so we get the two equations that we're after, right? Everything over here is a constant as far as everything over here is concerned, and vice versa. So now we have del squared F over F is equal to some constant minus k squared. And dt is equal to minus k squared alpha squared t. Okay. So this represents what we need to do in order to solve for basically thermal equilibrium, right? In a very, very simplified sense. And we can see right away that, well, a couple of things, right? So first off, what happens if this is steady state? So there are going to be a couple of things to notice. For steady state, what can we say?
dt equals 0.
Right, so dt equals 0. That means that if we go back to the original equation, what can we say about the spatial differential equation? What does that become in the case of the steady state?
Laplace's equation?
Right, so in steady state, this just becomes del squared F is equal to 0, right? So that's and that will be part of solving some of these problems. In the example that I'm going to send you off to do in a bit, you're going to have some initial conditions, and then you're going to solve the diffusion equation as it reaches a steady state, right? So if there's no time dependence, then it's just a solution of Laplace's equation. The general time dependence is kind of like back in E&M, or the first time that you looked at Schrodinger's equation, when you started adding the time-dependent part to it, it's just going to be an exponential, right? So the time-dependent part of this is going to be T of T is equal to e to the minus k squared alpha squared t. Okay, so those two things are true. In the steady state, it reduces to the Laplace equation. And as long, whatever you're looking at for time dependence with respect to this simplified version of how thermal energy moves, it's going to be an exponential solution. Okay? All right, so we have an example, which is also going to be your in-class problem. I'm going to set it up and then set you loose. So the example is the following. Suppose you have a slab. And for the point of this is just going to be a one-dimensional problem. So we're just going to have a slab that's going to be set so it has some temperatures. It'll have a length L, right? So we're only concerned with essentially the temperature as x runs from 0 to L. And at or after time t equals 0, we're going to let x equals L be held at 0 degrees centigrade. Okay. So the initial setup here, or what you're after, is that initially, let's see how I want to do this. At time t equals 0, we have x of 0 and x of L is equal to 0. So those are your initial conditions. After time t equals 0, actually, let me, I have this number here. These are your initial conditions. Basically, after time t equals 0, you have a steady state solution that this relaxes to, such that x of 0 is still 0 and x of L is equal to 100 degrees. So let me back up so that I kind of wasn't very clear about the setup of this. Initially, all right, never mind. Let me see. I was right before. Okay. What we're going to do is we're going to have an initial temperature distribution so that we start at, we're going to have a U sub U. And we're going to vary U from 0 to 100. After time t equals 0, we're going to have t equal, or x equals, x of L be equal to 0. So the initial steady state solution is d squared u dx squared is equal to 0. That's just Laplace's equation in one dimension, right? So what does u sub 0 of x look like? What's the Laplace's solution in one dimension? What form does it take? What kind of equation is 0 after two derivatives?
Constant.
Okay, that's one. So linear, right? Be linear combination of the constants, right? So this would be, say, ax plus b, right? Would be the general solution for Laplace's equation in one dimension, right? So given our setup, we're going to say that u of x is equal to 100 over Lx. Okay. Now, what we're going to do is, what I want you to do is find the general solution u. If this is what we're starting with, we're going to then release it so that sometime just after t equals 0, we have x of 0 equals x of L equals 0. In other words, your first step in this is to find the solution for f, right? Consider what that looks like with the general solution for t, and then combine those, and then you're going to set those equal to what your function ought to look like. In other words, you're going to find a general solution of u of xt, which is going to have to look like our u of x. Does that make sense? All right, I'm going to let you try this for a little bit. There's an example in the book that's a little bit like this, but it's a little bit more complicated. Your main goal here is to look at the boundary conditions. You should be able to find that what that f should look like based on Laplace's equation in basically one dimension. Then at time t equals 0, that will allow you to find, since that has to look like u sub 0, that'll allow you to find a general function of u. And ultimately where this is heading is that your solution should start looking like a Fourier expansion. So what you're after is this u of x comma t given these initial and boundary conditions. Clear? Let's try it and see where we get. So let me break out these rooms. And we'll take about 10, 15 minutes, and when you're done, or if you have questions, you can come out of the room. Okay, so let me do this. And as soon as your room is open, you can go ahead and jump in there. Okay, go to it.
Oh, we got kicked out.
Yeah. I didn't want you to spin your wheels too much. So, I mean, hopefully you got a little bit somewhere on this. I apologize, kind of muddled the explanation for this, but I want to go over this, the explanation of what's at the heart of this. How many of you got at least a little bit of the way solved for the X? Yeah? Okay. I mean, there are pieces of this that you can see your way through, is combining the idea that you have what it means to have a steady state solution after you have an initial condition that does depend on time. And I think that's where, and my apologies, I didn't quite explain it as well as I'd like to. So if we take the initial conditions, and that's not a steady state, that's just the initial conditions, we know that, so from the initial conditions, we have f double prime is equal to minus k squared f, right? That's just from the setup. So we know that from that, f of x is going to be the linear combination of sine kx and cosine kx. People get that? Okay. So the idea here is that because it's not a steady state, we can't just say that this is the linear, this is a Laplace equation solution. There is that time piece to that. And that means that we have u of x t is equal to e to the minus k squared alpha squared t a sine k x plus b sine k x. Okay, and most of the time that's sufficient for solving the problem, right? That's combining the, and in fact, in general, that is the solution, right, for heat diffusion. Okay, but then we look at what those initial conditions are before we release things and let them reach this steady state solution. At u of 0 at time t equals 0, we have this is equal to 0, so we know that b has to be equal to 0. We've seen that before. U of L is initially at 0 and then relaxes to 100 in this case. So that means that we have the usual argument case of L has to be equal to n pi. How many people got that? Ish. On the way? All right. That means that u of xt is now equal to the sum from n equals 1 to infinity of some constant a sub n e to the minus n pi alpha over L squared, all of this squared, because we're replacing our k and throwing alpha in there, times t times sine of n pi x over L. Okay. This is, let's see, 17, sorry. Okay, then at steady state, so the condition that we're imposing is that this reaches a steady state solution such that u is equal to this u naught, this linear equation that we had before. That means that for steady state, we have u, say, and just after time equals 0, since it's steady state, now we have, say, n equals 1 to infinity, and we can collect terms and call this suggestively b sub n times n times sine of n pi x over L has to be equal to u naught, which is equal to 100 over L times x. In other words, it has to relax to that imposed condition. All of this means that we're basically looking at a Fourier series expansion of that expression. All right, so one of the many reasons why we looked at Fourier series, why we looked at infinite series, is because this is going to come up in our solutions for many of these differential equations. And if you do this on this, if you do the Fourier series expansion of 100 over Lx on the interval from 0 to L, you can show that b sub n is equal to 200 over pi times minus 1 n to the minus 1 over n. And I'll let you try that, and maybe I'll post the expansion for that. But that's we've done what a linear expansion looks like in a Fourier series, and it's this sine series. Okay. Are there any questions about that? This is kind of a tricky use of initial conditions and then the steady state condition. And your book has one that's in 2 dimensions, actually. If you look in chapter 9.7, it looks at a plate, an X and Y that's infinitely tall and does essentially the same thing. It's just a little bit more complicated. It goes from minus L to L. Okay. Well, have a look at this, and I'll do another example and post it online because I think this is not necessarily an obvious thing, but it is an important thing. Okay. But it also shows that even in Cartesian coordinates, using the separation of variables can be kind of rich and tricky. Something you already know from Griffiths, I assume. Now, let's move on then to spherical coordinates. So in a nutshell, why is this more difficult or complicated compared to what we just did? Even in the most simple, that is, say, a Laplace equation, why does this suddenly become a lot hairier?
Because the partial derivatives depend on each other.
Right, and so what we have to remember is what del squared is for the different coordinate systems, right? It's not just d squared dx squared plus dy squared or dy squared, right? It's a lot more complicated. So let's let psi of r, theta, and phi be equal to some function of r, some function of theta, and some function of phi. And as an example, we'll look at the Helmholtz equation that we just looked at. In this case, that means that we have to look at del squared psi is equal to minus k squared, right? Ultimately. So what we've got is, after we've done this separation, excuse me, 1 over r squared, ddr of r squared, dr, plus 1 over capital theta r squared sine theta d theta of sine theta d theta plus 1 over phi r squared sine squared theta d squared phi d phi squared is equal to minus k squared. All we've done is take the prescription for Cartesian, but now use the spherical coordinate Laplacian, right? And immediately this becomes a problem, right? Because we have, even though we've tried to do this separation, we've got the variables all over the place, right? So the first step is to multiply everything by r squared sine squared theta. So that means that we can at least start with 1 over phi d squared phi d phi is equal to r squared sine squared theta. And I'll put this in brackets here, minus k squared minus 1 over r squared capital R dr r squared dr. Okay, so that's the r, that's the constant term, the r term, minus 1 over r squared sine theta, 1 over capital theta, d theta, sine theta, d theta, d theta. Oops. All right. So that's all a mess, except that all of that doesn't depend on phi, right? And that's our goal. So we can set this equal to minus m squared. Right? So again, that means that that azimuthal angular dependence becomes rather straightforward. It becomes a cosine sine term. So then we have 1 over r squared over capital R d dr r squared dr dr plus 1 over r squared sine theta d theta sine theta d theta minus m squared over this r squared sine squared theta, all of which is equal to minus k squared. Okay, so if we multiply through, we get, just trying to simplify things, 1 over capital R d dr of r squared dr dr plus r squared k squared. So now we've got our r's all in one place. This is equal to minus 1 over sine theta, 1 over theta, d theta of sine theta, d capital theta d theta, plus m squared over sine theta. And again, the goal is to separate things out. And it doesn't necessarily mean that what we have is something obvious, right, to solve. But we can start down the road, and this is the justification for why we care about these special functions. So A23 here is key to understanding things like Laplace's equation, like Schrödinger's equation, like many things. We chose to start with the Helmholtz equation because it allows us to just focus on the Laplacian. Right? So if we look at these different terms, we can say, look at 1 over sine theta d theta sine theta d capital theta d theta minus m squared over sine squared theta capital theta plus, say, q times theta is equal to 0, where we're identifying functions. Basically, this equation is, or the generating equation for, or this is the associated Legendre equation. The solution to which is the associated Legendre polynomials. On the other hand, 1 over r squared d dr, r squared dr dr plus k squared capital R minus now that q, where we've just collected terms, times r over r squared is equal to 0. This represents what are called the spherical Bessel, or the spherical Bessel equation. The solution to which are the spherical Bessel functions, right? Specialized functions that have no closed form. They are aperiodic, but oscillatory, right, as we'll see. That means that we can write Oh, and we also have, of course, 1 over phi d squared. The only part that's easy, right, is this part equals m, right, or m squared. That means that we can write psi of qm of r, theta, and phi is equal to the sum over q and m of some linear combination constant of r sub qm of r, theta of qm sub theta, and phi of m, double phi of m, of phi. This is our nasty solution, right? And how we deal with this basically how we typically deal with this is look at special cases in which we can take care of symmetry. None of this should look obvious, right? We have the differential form and we separate it as much as we can. But in order to recognize, I mean, in past classes, perhaps you've gotten as far as this, right? And then focused on very specific examples. What we're going to be doing is looking at since we recognize these equations, in fact, in the last homework and in this homework, some of what you've been looking at, the reason why I've had you look at things like the Chebyshev equation, the Legendre equation, associated Legendre equation, Bessel equation, is because where it was headed was recognizing those equations in these things right here. And then if we know what the solutions are to those differential equations, we can make something we can at least recognize the solution to a physics problem. So as a quick example, I can start this up. Suppose we have a homogeneous spherical solid with constant thermal diffusivity. That means K, and no heat sources. What do we do? Well, that means that the differential equation that we're looking at is du RT dt is equal to K, the diffusivity constant, times del squared times U of RT. And so we can write this as U is equal to RT, separating out, in this case, it's just spherically symmetric. That means that R dt is equal to K times T del squared R, 1 over KT dt is equal to, again, we have to be careful of this, r squared ddr, r squared dr. Again, one side is constant with respect to the other, so we might as well set that to something that'll help us, say minus alpha squared. And then if we factor things out to make it a little bit more reasonable looking, 1 over r squared times 2r dr plus r squared d squared dr squared. Right, we've basically just rewritten what this looks like. This equals r squared d squared r dr squared plus 2r dr is equal to minus alpha squared r times capital R. We already know what the solution for t is, right? As always, that's going to result in our typical time dependence. What this means is that we're left with r squared d squared r dr squared plus 2r dr plus basically alpha squared r is equal to 0. And what will come, this is essentially what leads us to our spherical Bessel functions, and we'll look at next time spherical harmonics, where the Legendre polynomials come from all this mess. We've gone over time because I know there's a lot of derivation here. So what I'd like you to do is just write in, submit a reflection about differential equations. And if you want more examples of separation, that's great. I'm happy to do that. We're kind of halfway through some of this separation stuff. I really encourage you to read chapter 9, especially the latter parts of chapter 9, because they go through these different equations. The key to being able to do this is that we're going to look at the 3 different kinds of geometry and taking advantage of special cases in which there's symmetry that we can take advantage of. Is it spherically symmetric? Is it cylindrically symmetric? Oftentimes, all of these pieces are going to drop out, right? You're familiar, I'm sure, with spherical harmonics. That's where we're not even looking at the R part, and we're looking at what is the solution of y Lm, right? That's what this is coming from, or where this is headed. But what A.28 is going to get you is what are called the spherical Bessel functions. Again, non-periodic but oscillating functions. And while they're not something that you normally see every day, what you should keep in mind is that they're no different from using sines and cosines in Fourier series, okay? They're just going to be a linear combination of functions. We're just used to seeing sines and cosines. They're just not going to be sines and cosines in this case. And with the other cases that we look at basically Monday and maybe a little bit into Wednesday. Okay. All right. So please submit your reflections for all this week, all of it. Doesn't have to be long, but just please do it. And let me know how you're doing, okay? I'll get your homework graded and back to you as quickly as I can. All right? Okay. See you guys.
Thank you.
Bye, Adrian.
Bye, Stephen.
Bye, guys.